Okay, so what I want to do is I just want to do one example problem because there's so much you can learn from these problems. Yeah? So what you have is a dielectric, so I'll take this to be my z-axis as usual, and the entire bottom part is filled with a dielectric. Okay, so this entire region is a dielectric of with permittivity epsilon. This is vacuum over here, so the permittivity is epsilon naught. You can see that this is nothing, eventually going to be an image probe. So instead of a conductor, you're filling the universe up with a dielectric, but you're placing a physical charge Q, a distance d above the z-axis. And you want the potential everywhere. You want to know where the charges are, and everything you would want to know. Okay, so let's sort of try to get the plot right, and I'll go through this slowly. And these are all, not that it's difficult, but I just want to go through it in detail, and I have nothing else in mind to do. So in this region, okay, where the dielectric is, so let me make that clear. What you have is, first of all, divergence of E is equal to epsilon rho over epsilon naught, and this is of course rho free plus rho bound over epsilon naught. But there's no free charges in the bottom half of the universe, so this is just rho bound over epsilon naught. On the other hand, I should make this clear, this is a linear dielectric. On the other hand, divergence of E is equal to divergence of D over epsilon. Well, it's the other way around, in the sense D is epsilon times E. And so I can bring the epsilon out because in this entire region, I'm not worried about the boundary at all. I would get divergence of D, which this is nothing but rho free over epsilon. But there are no free charges here, so divergence of E is 0. So when I combine these two, I get the fact that bound charges, charge density is 0. But that does not mean that there's not a surface charge density. This can induce a negative surface charge density. Well, if it is there, sigma b is p dot n. In our case, it is p dot z hat. But the polarization, but it's the uppercase, so it's the polarization per unit volume. This is epsilon naught chi e electric field dot z hat, or lots of notation, and partly why I'm doing this problem is to recall all of these terms. I don't wish for you to commit these to memory. I don't. Every time I have to teach it, I sort of revisit it. So if you make good notes, you will know how and when to access this. Okay, so let me make all of that very clear. So over here in the diagram, we might have some bound These are all the charges. So what we want to do is understand what this EZ is. Okay? So that we know what the sigma bound is at the boundary. I'll of course call this below and call this above. And in this picture, which I don't want to lose the essentials, let me also write the boundary condition that I'll need. Oh. Thank you. Right. I'm partly, your thoughts wander, so you just write.
We're close to Friday.
Close enough. Yeah. So the boundary condition will need d perp above minus d perp below is equal to sigma free. See, I used d because it tells you sigma, it's based on sigma free. And that I know is 0. If I put it as if I used E, there's a similar version with E, I won't get 0. But that also can be handy. Okay, so what I want to do is get, suppose you have a charge here, right? Some sigma. What I want to do is get the electric field right here on the surface, because that is what I would need. And with this in mind, I want to get the electric field right from above and right from below. So my goal is need E perp above and E perp below. For all, D is proportional to E, that's why I need all of this. So what I'm going to do is I'm going to look, I know there's a sigma bound here. I'm going to break this into 2 regions. I'm going to make this a small patch, yeah? And I'm going to call it patch. And this region, I'm going to call it outside. Really, I'm going to call it outside, but I mean outside the patch. And somewhere along here, I have a Q. So I'm not looking at this patch right below Q. I'm going to look at it all over the XY plane. Yeah? So whether it is above or below, well, okay. So E perp at Z equals 0 is going to be, it's perp, so I don't need to put that, the vector sign. E perp due to Q. There's one term, I'm not saying this is the only one, due to this guy. Plus E perp due to patch. Plus E perp outside the patch. And if it's above I want, I'll put above 3 times, 4 times. If it's below I want, I'll put below 4 times. But then I know these are the things I should be looking for. Travis, are we good? Yeah. There could be nothing else. We've accounted for everything. Now, I'm going to look at the center of this patch. From here, if there are charges over here, which way will the electric field be? Well, positive charges will pull or push, and negative charges will push, right? So to speak, or it's the other way around. Positive charges will push, negative charges will pull. But the point is, if these charges are over here, it's only going to point in this direction. I don't care about that at all at the moment. I'm only worried about the perpendicular component. So I can say this is going to be 0. Why? Outside charges can only create a horizontal
because they're on the same plane.
They're on the same plane. Yeah? Okay, I need one more piece of the puzzle, and then we're ready to go. I want to get E due to the patch. So I'm going to zoom in on the patch. I've just magnified and magnified and magnified, okay? So in that small patch, is the electric field constant? I'm just zooming in a dot, practically a constant, yeah? And if you're in the center of this patch, what do you see? You see an infinite plane, yeah? Well, you see a flat earth, don't you? Same thing. So that means if this is sigma, and I'm going to call it sigma bound, due to the patch, I'm going to have this, which is E equals sigma bound over 2 epsilon naught z hat direction. If it's negative, it'll be negative, and over here, it's E negative sigma b over 2 epsilon naught in the z hat direction. This is, be careful, above. And I'm putting all the ingredients together. Are we good? Okay, so this is 0. This one we figured out. We need this one. See, Q is far enough away from this, you won't find any discontinuity. Discontinuity occurs when the field is created by some surface charges. If you have a charge over here, it's KQ over R squared. That's not discontinuous, far away. So this I won't have to write up or down. Huh? And of course, I need this component. This is some theta. So this is also theta. I need only the perpendicular component. What do I mean by that? That is going to be E perp. Are we good? Okay, well, it is KQ over R squared, and then we need to find the component of this. So E perp, let me do this so that I have space. E perp due to Q is equal to, first of all, it's pointing downward, minus KQ over R squared. I can write this where S is my cylindrical distance, huh? X squared plus Y squared. But I don't need all of it, I just need cosine theta. I just need the cosine theta component, the perpendicular component. What is cosine theta? I can look at this. Cosine theta is this over that. So that is minus KQ D S squared plus D squared S squared plus square root of S squared plus D squared. Are we good? Okay. Gosh, at some point, since we need space, I'm going to start erasing. What I'll need mostly is E perp below, but I'm going to write E perp above and E perp below. So E perp is equal to 0, and this is above. And that's going to be minus K Q D S squared plus D squared to the 3/2 plus sigma bound over 2 epsilon naught, correct? These two. And E perp below, see, what changes?
Sigma bound.
Yeah, that's it. That's it. Any questions so far? I'm going to erase this. So I had sigma bound is epsilon naught chi E Ez, which is the same as E perp, and this is from below. So I get sigma bound is equal to epsilon naught chi E, and that's Ez and E perp is the same. That's precisely what I calculated. I'm going to bring out the negative sign, which is reasonable. If you put a positive charge over here, the dipoles are going to align, and the negative is going to be on the top. And these two, K, Q, D over S squared plus D squared to the 3/2. And look at that. Well, okay, let me just leave the negative here. I can bring it to the other side. Sigma bound. So sigma bound is given in terms of sigma bound. Well, that's okay, I can solve for it. We can do algebra. Sigma bound, I have 1. This becomes a plus epsilon naught chi E over 2 epsilon naught equals minus epsilon naught chi E KQD over S squared plus D squared to the 2/2. The epsilon would cancel, so I would get sigma bound is equal to minus, what is this going to be? That I have epsilon naught, I have a chi e over here, and then I have 2 plus chi e, and then I have a 2 over here, so I put a 2, then I have k, which is 1 over 4 pi epsilon naught, q d over s squared plus d squared to the 3/2, and we will make sure that we check the math. The epsilon naughts would cancel. I have minus 1 over 2 pi chi e over 2 plus chi e qd over s squared plus d squared to the 3/2. So let me write that so I can erase the future. Minus 1 over 2 pi chi e over 2 plus chi e q d s squared plus d squared to the 3/2. We've done a good bit of algebra as well, and I'm walking and talking, so let's make sure that I haven't made a mistake. Well, yep, we got lucky. Everything works out just fine. So we have managed to get the sigma bound. So the further out, so the most amount of negative charge is right below here, where S is equal to 0. And as the distance increases, what happens? It decays. That's good. You don't have an infinite amount of charge. Are we good? Yeah.
So can we go back to sigma bound in terms of EZ? When we said if we got it from P dot n time, we said it was positive Z that direction. So why are we looking at EZ below?
EZ below doesn't mean the bottom component. It just means the component of the electric field in the Z direction. From below, because that's where the dielectric is.
Yeah, okay.
Yeah.
Yeah.
Yeah? Good question. Fine. Your textbook integrates this out to get a total bound charge. How much is this sigma bound? Is it the same as Q? Like it would be if it's a conductor, but it turns out it's not. The dielectric often weakens things. So the total Q bound, well, it's nothing more than sigma bound integrated over the area S squared, S ds d phi. And when you do this, this is an easy enough integral. Look, although you have S squared over here, what's the, it's 2s ds is the differential of this guy, right? If you did a U substitution, you have the S over here. So let me, in good faith, yeah, it's minus, of course. That's what is going to end up happening. Okay? That's the total bound charge. Fine. Now, we want the potential everywhere. In one sense, it's easy to write down. It's difficult to integrate. Unless you guessed it, image charge. But let's write down and see what we can learn from it. I don't care where the potential is going to be calculated, upstairs or downstairs. I don't care. But I know this is going to be KQ over R1, where right, KQ over R, plus sigma bound by K dA over dA over R. Which means what? R is going to be from some, let me put it over here, dA to this point, right? It's going to be this vector from the dA region where the charge is all the way to the point of interest. So it's from the charge to the point of interest. In our case, from here maybe even to here. I draw that one. But yeah, you can integrate this all you want. We're not going to use this. Save one fact. We'll just need one fact. As Z approaches plus minus infinity, what do you think happens to the potential? What do you think this is going to do? Zero.
Well, that would go.
I'm sorry?
That would go.
This will go to zero, so the whole thing goes to zero. Here too, sigma is also decreasing along the integral, but then you have a distance. If you're over here, I don't care where it is, the distance is increasing. The distance is the smallest here. Obviously, anywhere else it's even greater. And even this distance is becoming smaller and smaller. So we clearly have V approaches zero. Yeah? So what I'll do is I'll erase all of this and write boundary conditions for potential. B-O-U-N. I'm going to break it into two regions. What are the boundaries for above? There are two regions. One is this guy. Yeah? And the other is, of course, this guy, where this is Z approaches infinity. Here we know the answer already. What's the potential? Zero. V equals zero. Here, we don't know the potential, but we know the derivative of the potential. Yeah? We know that minus d above dz, that's what this is equal to minus k q d over s squared plus d squared to the 3/2 plus plus sigma bound over 2 epsilon naught. So either potential or the outward gradient of the potential is defined on the boundary. What were the conditions for uniqueness theorems? Precisely that. So if we can find a solution satisfying these two conditions, we have found the solution. Of course, if we find a solution satisfying when I say satisfying, is that a what?
Fine.
Yeah? Okay. V approaches 0 as Z approaches infinity. No, I was not questioning you. I'm just amazed every time I figure out spelling. And I'm going to call this equation 1 and equation 1. Uniqueness theorem says if we find a solution satisfying V goes to 0 as Z approaches infinity, and equation 1, then we have the solution.
Do we not still have to find, like incorporate in that sort of Q exists in that space?
Right, so solution satisfying what? Del squared V equals,
Throughout that function?
right, Q times delta, what's that, Z minus D. Over epsilon naught, I forget. Is it minus rho over epsilon naught? Yeah, it's minus, because E is the negative gradient. Yeah, it has to satisfy this, not Laplace's equation, but rather the Poisson equation. The same argument applies to below, except the only thing is, this is being replaced with this. So I'm just going to say, you know my notation, right? Similarly, the analogous statement. V has to be 0 at negative infinity, and on the boundary, this should be the derivative of V. If these two conditions are met, and of course, in the lower half, it is Laplace's equation, because there are no charges. If we can miraculously find it, we will have found the solution. So you look and stare for a while, and you use the only thing you know about image charges. If there's one on the top, you place one on the bottom. And that's exactly what happens. I derived this in a different way. We found that Q bound right? We had this result as well. Okay. So this begs for yeah? Okay, I'm going to erase all of this. Bottom part, top part is easy. The bottom part requires a little bit of guess. Okay, so let me write this. V above. that's easy. First, I have a real charge. So KQ over R. X squared plus Y squared plus Z minus D squared. Correct? Obviously, what am I going to do? I'm going to go D here, except I won't place Q. I'm going to place Q bound. Yeah? Because divergence of E in this region should give me Q bound. It'll occupy this one, right? So I won't place Q. Place Q bound. And what does the potential then look like? Plus KQ over X squared plus Y Q bound C plus D squared. Correct? Okay, V below. There's a problem. I'm writing the potential here. Can I place any charges here? No. So what do I do? But I need to see the same QB in the boundary. I'm going to take it and stick it over here and see if it works. After all, this is a guessing game. What everyone should understand is, in writing this expression, for above and below, I have not added a charge. If I'm talking about above, I have not added an image charge above. If I'm talking about below, I have not added an image charge below. Image charges are not real, so I cannot place them in the regions of interest. Yeah? James. I'm not saying we have the correct answer. As long as uniqueness theorem, because we have uniqueness theorem, I can write anything I want. I just have to show the boundary conditions. Okay, so let me do one thing. So D perp above minus D perp below is sigma free. We don't have any free charges, so I'm going to write this as D0. But D is epsilon times E. So, and above, I have epsilon naught E perp above. And that's equal to below, so equal to epsilon E perp. Correct? I can do slightly better. Minus epsilon dV above over dz is equal to minus epsilon dV below dz. You can play with all you want. If I get this to work out, we're good to go. Then the boundary conditions will be satisfied. They're all coming from the same place. All I have to do, evaluate it at z equals 0. I mean, of course, that's where the potential derivatives. And I can get rid of the. I want to take one derivative to show so that I can skip steps. If I have v equals kq over x squared plus y squared plus z minus d squared, let me take the derivative. What is dv dz? It's kq. I'm being sloppy here. This is not part of the main narrative. This is minus 1/2, so I get minus 2, and then I get x squared plus y squared plus z minus d squared to the 3/2. Then I get 2z minus d. And then I let dv dz z equal to 0. I get minus kq d. Not c minus d, but rather. Yeah, I just took a random one. So now I can quickly apply over there, okay? Gosh, I don't know where I'll write it. But maybe I'll do it here. Remember this. This is what I'm trying to do. Epsilon naught. I'm going to take the derivative of the above. We just did that. If it's a minus, I get minus kqd over, again, I'm going to use s plus d squared to the 3/2. Over here, what do I get? Plus kqb d s squared plus d squared to the 3/2. That should be equal to epsilon times this guy. This is both minus, so I would get a minus k d q plus qb over s squared plus d squared to the 3/2. Correct? All I need to do is solve for QB. Because here we just called it randomly QB by guessing it. If we get the answer to be this, we're good to go. Everything else will just work out. So I have K, D, I'm going to cancel this from every single term. I have epsilon naught. And what do I have? QB minus QD is equal to minus epsilon, no, sorry, QB minus Q, have Q plus QB. Or epsilon naught QB minus epsilon naught Q minus epsilon Q minus epsilon QB. I'm going to bring all the QB to one side. Epsilon plus QB is equal to minus epsilon minus is that true? I hope this is correct. I'm going to do epsilon naught plus epsilon naught chi e minus epsilon naught divided by epsilon naught plus epsilon naught plus epsilon all the epsilon naughts will cancel. And indeed, I have minus chi e over chi e plus 2. Of course, again, so many definitions in all of this. Epsilon is epsilon naught. So we get, if we just blindly call it QB and solve it, we get the same answer. Now you can go back and see that the boundary conditions are met. So we have the unique answer. So for the top, you place the image charge on the bottom. For the bottom, you place the image charge on the top. Where else can we go? Very good.